Okay, thanks. Thanks everyone for joining. It's already 10 minutes past 3. Of course, requested to allow others to join. So I won't take much of your time. I'll take you through a preface of a course that we offer that is in our training on AutoCAD and introduction to surveying using GNSS. So in this course, we're just going to have a look at a few things. That is the introduction of course spaces. Look at some of the techniques in surveying and applications. Basic operational fundamentals to use AutoCAD. And then we are just going to highlight some of the things we can do in 3D modeling and data management. And then later on, we'll organize another online session to purely discuss 3D modeling and data management. So just to introduce you to EcoSpace Services. It's a geospatial firm that focuses or specializes in providing geospatial solutions, offering both as a service, sale of surveying equipment, training, application development, and internship to students. So we offer hands-on training that is on practical sessions. That is when you're dealing with surveying equipment. And then you also look at updated skills. We train you on the skills that are today's demanding, so as you conduct your normal J work activity. So the reason as to why we think that you should be able to work with us. So we're not just looking at you from the perspective of undergoing the course and finishing it, but we offer the practical field-based training. So we have a classwork exercise. After the classwork, then we attend the field work. Then you'll be able to learn whatever you have, be able to practice whatever you've learned in class. Industrial experts. We have all trainers for different professions that are able to take you through your specific needs. So the courses are tailor-made for specific needs. If you want a course in GIS for modeling, if you want a course in GIS for human resource management, for natural resource management. So that's why you have different experts in different fields to be able to handle such kind of courses. So look at the global relevance, that is. Our courses are currently being underscored by NITA, so that at the end of the day, after joining each and every course, we can give you a certificate that is NITA approved. For that, as earlier mentioned, we offer career advancement that is specifically to students to help them understand and come through whatever they've learned in school to put into practice. So just look into some of the surveying techniques and applications. This is just an highlight of what you expect more when you join the course or when you decide to undertake the course. And these are some of the challenges that maybe you might be facing. So in this course, we all understand that surveying is evolving. It's not like 20 years ago where there was a chain. I understand that there are some places that people still use chains. Where you're supposed to do a subdivision, you have to pace, determine the distance. So the course is built for understanding from the basics measurements to advanced technology using GNSS and illustrations. So we cover both parts. Apart from that, in our courses, we understand that doing the exercise is very easy as long as you've learned it. But in our course, we emphasize on the why. You need to understand. You need to understand as to why something is happening, not just how to do it. So in most of particular issues or training, you're being told how to do something, but you're not being told why you're supposed to do that. So if I change the parameter from 10 to 2, what is the effect? So you all need to understand the why behind it, and that's why we are looking at the surveying techniques and applications, just highlighting what is important is covered and what you need to know when you decide to join our courses. So there's something called centering and leveling effects. People, somebody, it might look simple, but did I center correctly? Or did I level my tripod properly? But as I said, we're not looking at how do you do the leveling or how do you do the centering. We're looking at why you do it. And if you made an error, what would be the error come to in the results? So somebody can ask a question, does any slight of centering or even poor leveling affect your results? Of course, the answer would be yes, but the question is, where in your results is that effect going to be applied? So on the screen, I have a drawing. This is assumed to be a beacon. So the black dot is where the nail is. Okay? The black dot is where the nail is. So when it comes to centering, it means that you're supposed to set up your machine, ensure if you're using the bulb, if you're using the laser light, it's supposed to be on top of the black dot. There's something also called tolerance. So if you are able to do that, and then I've added some 3 dots, one person might be on the first dot, the other person might still make it on the second dot, somebody might be on the exact dot where it is. So at the end of the day, you are off. But the question is, however how small it is that you're off, let's say you're off by 3 centimeters, not 3 centimeters, but 3 millimeters. But when you are centering or when you're doing a leveling, you're off by 30 seconds, 30 minutes, I mean, 30 seconds, yeah. So the question is, can you determine where that error is coming from? And after determining where the error is coming from, can you also identify the effect it's going to cause on your work? Because teaching somebody how to do it, it's very easy. Teaching somebody how to do the leveling is very easy. But knowing how the human errors affect your results and the implications they can is the most significant thing. Someone in the background? Kindly unmute. Who is talking?
Sorry for that.
So how do you correct and account for such human errors in your computations? Genesis of information. Even before you correct for them, before you can decide to account for them, the question is, how do you determine that you've made such an error? Does the software give you an opportunity to be able to evaluate to say that your work has an error? Does it meet the threshold? And if it does add an error, of course, no one is perfect. But another point is, how do you compensate for that error in the application? Or you just process the data from the beginning to the end without identifying where the error is? So with the current technology, it is not as before where you just process your data, you submit it where whoever wants to do it, and then that is it. There is what we call the lasers to be able to determine if a building is straight. When you go to a construction site, the fundis will tell you they're using a kabir. But nowadays, there's the lasers distance measurements that can determine if a building is straight. And that's why I was saying we need to look at what we call the 3D analysis in surveying, in sectional properties. Why do you need a laser scanner to do your sectional properties? So the current technology where we are using the lasers are so much accurate to an extent that 2 to 3 centimeter, or 2 to 3 millimeter is such a big error that can affect a building to fall down, or can change your direction of movement, or can affect the distance 30 seconds. So when you join the course, that is a introduction to surveying using GIS, these are some of the things you'll be able to look into. Apart from just seeing how the data is collected, where do you correct that in the software? How do you account for it? Another thing that people fail to look most often is what we call the scale factor. When it comes to maybe when you're plotting, or maybe when you're making measurements, a question I would ask is the scale factor effect on distance measurements? If you've used AutoStation, you've used a GNSS equipment, you've even used a tape to make some measurements. In one way or another, you'll find that when somebody make a measurement on the same distance, let's say it is 100 meters, you'll never get exactly 100 meters. It's either you get 100.005 or 99 plus something. So the question is, where is that coming in? Is it that the tape has been extended too much? Is that the tape has an issue? But that is if you're using a tape, that the tape has a sag. But what if you're using a GNSS equipment? What if you're using a AutoStation, where the laser beams are being sent and reflected back? You need to understand or look at what does this effect apply on. Somebody will say, how does a AutoStation measurements has a scaling effect? If you've used AutoStation more often, there's always what we call the scale factor, or the ground and grid distance measurements. I'm going to talk of coordinate systems in the next slide, but before I get to that point, there's what we call a grid and a ground. In primary school or in secondary school, we had to plot. We have a 3D representation of a feature and a 2D representation of a feature, where you have to plot something on a paper. And then you say you're moving 2 meters X and 3 meters Y. So that is a grid. So that is what we call projection. You are taking it from a 3D representation to 2D presentation. So you're taking it from 3D to 2D. In any measurement, as long as you started doing transformation, you're introducing errors. When the laser is traveling from one point to another, there's refraction. The light has to be bounced back. When it is bouncing back, the time taken is what is being used to measure the distance. There's always what we call the scale factor error of 0.9996. When you do a ground measurement and when you use a GNSS receiver, knowing when to use the 0.996 or 1 is very key. So somebody might say that this is a very small, if I round it off, of course, it is 1. So the difference between that is 0.004. 0.004 might be very small for somebody. When you visually look at it, but when it comes to computations, when it comes to, especially when you're doing engineering survey works, this is very key. It is said that a surveyor should be in the site from the beginning of any construction, and he or she should be the last person to leave. So you should ask yourself, why would a surveyor be in the field from the beginning to the end? It is because of this kind of thing they're supposed to check. An example would be when the bridges are being constructed, then poles have to be raised and then fixed on a specific space. So imagine if you did not cater for the 0.099 and then instead you use 1. the alignment is totally going to be off. So in that particular, if you look at it in that particular case, you are going to see the importance of it. But somebody would like say that that is very minor, but look at it in the context of a long distance. So it will continue to pile up. Then by the end, you're getting to a chain edge 0, maybe chain edge 1 kilometer. It will not be 0.996, but it will be more than a centimeter. So the longer the distance, the higher the enough base. Another thing or technique that we look at mostly is somebody says he's working and he has a float solution or even has a fixed solution. The bare basic question somebody would ask is a fixed solution better than a float solution? They are all solutions. What I can say is it depends on which kind of work that you're doing. It's not that one is, well, of course, one is more accurate than the other. But a planner using an handheld GPS receiver to get a position, and a surveyor using a GNSS receiver to determine a position. If a surveyor determines the same position that the planner picked, if a surveyor collects a float solution for that point, and a planner uses a handheld, a surveyor will still be more accurate than the planner, though the surveyor got a float solution. So if you're comparing fixed and float, fixed is best, yes, but it also depends on which kind of activity you're using. So I'm actually making this presentation based on some of the FAQs questions that we get regarding the usability of some of the questions. So a float solution, initial position can be estimated as less accurate as compared to a fixed solution, where the position or the point has been corrected for the errors. In the diagram on the left-hand side, you see a blue dot around the globe, and also see somebody moving. Also around the globe, you are seeing satellites, but on the sky, rotating. So you see the blue dot at one particular point, it has 9 satellites, 8 satellites, 10, it keeps on fluctuating. So that is you're walking. At one particular point, when you're obstacles, you're seeing small satellites, lesser satellites. When you're in an open space, you're seeing more satellites. So for you to determine a position, you must have at least 4 satellites for your position to be given. But in this particular case, when you come to a solution, you're looking at a fixed solution and a float solution. This happens when you're receiving corrections from a base station. So for you to be able to have a fixed solution, your base must be able to see at least 4 satellites. And you, as the roving person, must also be able to see at least 4 satellites. Those 4 satellites that the base is seeing, you must also be able to see them as the rover at the same second. If that doesn't happen, then you don't have a fixed solution. But remember, you can still get a float solution, but you're seeing satellites, can be seeing more than, your receiver can be able to consume more than even 10 satellites. The base can be even consume even more than 20 satellites, but you're still getting a float. Why? There's multipath. There's maybe out of all those, there are at least 4 satellites that are converging. Your time synchronization at that particular moment. There's maybe a cloud that is obstructing you. So the point here is, these are surveying technique that somebody is doing. These are surveying technique that if you see this error, you need to know why is it coming, where is it coming from. There's another thing that I don't know if people still remember it. PPN. That is what we call the part per million. When you look at a brochure, When you look at an GNSS, they tell you that this machine has this accuracy to 8 ppm. Talking of a base and a rover, nowadays you use post stations. Somebody is going to set up his base, then he starts working. As long as he cannot go more than even 10 kilometers, majority of people start complaining that, oh, this rover is not, your machine is not working properly. Why? Because there's not more distance than another person. The issue is not the distance that you're supposed to go. The issue is what accuracy do you get the more distance you travel from the base. Part per million means how the measurement errors that you are observing grows as you move away from the base. So it means the more you are from the base, let's say if you're 1 kilometer away from the base, the error you are likely to introduce into your measurement is 1 millimeter. So imagine you are 30 kilometers, as people complain that the base, the rover base distance is left. You're 30 kilometers from the base, that is 3 centimeter error. You never did your centering correctly. That's another 3 centimeters. So you have 6. You're getting a plot solution. Then you want to do at the end of the day, and then you say that maybe your work is wrong. Maybe the machine plots has an error. So every work that you do, it's correct. The question always is, can you be able to justify your answer and convince somebody that, yes, my work is right because of ABC? At the end of the day, know your equipment better than it knows itself. Know that when I key in 4, I'm expecting to get 6. When I key in that, I'm expecting to get ABC. So the key takeaway when you join the course is how you're going to learn how to interpret the GNSS results. When to accept a results or when to reject the data. Ensure there's a professional precision in your results. On this part, I'm going to leave you guys with a question. There's a difference between accuracy and precision. So would you say that my work is this precise? Or would you say that my equipment is this accurate? Or would you say, how would you differentiate between a job that is more accurate and a job that is precise? Or do we use precision for equipment, or do we use precision for a work done? Or is it the other way around? On the same note, when it comes to precision and accuracy, people always say that I want to take my GNSS receiver for calibration. If you can calibrate your GNSS receiver, then it means that you can also calibrate your radio. You can also calibrate your phone. You can calibrate. In essence, what I'm trying to say is, in the GNSS receiver, we only have a motherboard. So we do not calibrate GNSS receivers. There's something called the antenna phase center, which is what is just being worked on to ensure that these errors that we are talking about here are reduced to the bare minimum, as recommended by the manufacturer. So having looked at the fixed and the float solution, another technique or something to be able to consider mostly when you're working with the surveying is the coordinate system. In this particular area, in Kenya, people use up 1960, almost in every part of the country. Up 1960 is the projected coordinate system. The geographic coordinate system is WGS 84. So if you use a wrong one, then you're going to have some shifts in your results. So key thing to note in that in the machines that we're using, you need to be able to know what transformation parameters is the right one to use at that particular point, particular location where you are. So in Kenya, there are 3 transformation parameters. We have one called Act 1960 Kenya, which are negative 157, negative 22, 29. You have one called Kenya stroke Tanzania, negative 160, negative 8, and negative 300. And then you have the mean, which is negative 160, negative 6, and negative 302. The question is, or the point here is, they are not all wrong. They're right, and that is why we have 3 of them. Where you know, or where can I use one, and where should I not use the other? That is the question should be asked. And if you use the wrong one, imagine you've placed a beacon using Kenya. Somebody else comes and use the same beacon, then place another beacon using mean. That is how our errors always start moving from one point to another. The other issue comes when you're doing transformation. The coordinate system that you have is in Cassini. You have Cassini coordinate system. You want your GNSS to be able to use Cassini coordinate system, which is okay. You can be able to use Cassini coordinate system. So you want to do transformation from Cassini to UTM or vice versa from UTM to Cassini. So the question is, first of all, majority of the GNSS equipment can currently do that, but it's the process that we follow correct to ensure that we limit the errors. The most fundamental question at this particular point is the process followed. Anybody can move from point A to point B, depending on the routes that they choose to follow, but they will get to point B. Some people will take 10 hours, some people will take a shorter time. So depending on the route that you follow, it will determine how accurate you get or the time that you take to get there. Remember, your GNSS receiver by default, it receives positions in WGS84. The moment it receives corrections in WGS84, you don't interpret corrections in you interpret corrections in UTM. So by default, most of the units are in UTM projected coordinate system. At the same time, you are seeing UTM projected coordinate system, you want to do transformation to Cassini. Not knowing that the equipment has already done transformation from the WGS84 to UTM, then now you want to do from UTM to Cassini. There are 2 transformations that are being involved in that. So people tend to assume the fact that the GNSS receiver is already doing transformation on the fly. So that's what I'm saying. Know the process correctly. Another issue that always happens when it comes to the coordinate systems, and I've seen this most often, or it is a question that I've been asked several times. People experience an issue that is called the base shift. You're doing your work, and then all of a sudden you get a notification from the rover that the base has been moved. So the question is, of course, the base, as you are the one who set it up. By the look of things, the base has moved. But why then the equipment has to tell you, notify you that the base has moved? So in that particular case, you just need to recall the steps that you followed, then identify or find a solution as to why it says so. We can be able to sort that out as well during one of those our courses. So at the end of the day, what are you going to take out from this? So learn how to choose and transform your coordinates properly. It might look very simple because maybe the more you are used to doing something, when somebody gives you a machine, just say, I just keen on this. But you see, on the list of what you need to choose is just up 1960. But it will not display for you whether the parameters. So you might miss that. Practical exercise to confirm projections that matches with the national standards, then using a wrong version that leads to misalignment, or to reject the results. So that is on coordinate system. The other key thing on surveying techniques, let's look at leveling and traversing. So I was asking myself, or somebody was asking me that, can you use a total station to do leveling? We always use levels for leveling purpose. So somebody was like, Fred, can I use a total station to do leveling? I told him, yes, you can use a total station to do leveling. But the question is, how are you going to do that? By setting up the total station carefully and using trigonometric leveling techniques. You can be able to be shown how to do that, or I'll be able to show you guys how to do that. We have an offer coming up for you. I asked someone one day that when you're running a traverse, you do run a traverse in a zigzag manner. But before GNSS came into play, people are using total station to do their work. Not even before total station came in, they started from the chain. Then from the chain, we went to theodolite. People normally don't talk of theodolite nowadays. Then total station came and then they replaced theodolites. Nowadays, total station is less, I say on a scale of 1 to 10, maybe 1 used, mostly in engineering, surveying work, yes. Total station is being used. But majority, we've replaced total station with the GNSS. But the question that we ask is, nowadays, when you want to transfer control from one point to another, you just go and set up your base stations, densify controls within your area of work, do static observation, then process your data. But in the older days, we used to run traverses, but the traverses were being done in a zigzag manner. The question is, why is the GNSS receivers not applying or not using the, or why was the total station used? Why was traverse being run in a zigzag manner? Of course, the answer is to reduce the cumulative angular errors that can occur when you're doing your computations. That brings me to something called error ellipse. You can look at it to be able to understand what error ellipse does. But we are transforming from total station to GNSS. Where is this? How does technology handle this kind of an issue? There's something called dilution of precision. This is the relationship of zigzag manner of running a traverse, so it is being brought for GNSS. GNSS, there's so many adjustment computations that are being done in the background to ensure that you get a good results. And that is why from the beginning I mentioned that you must have at least a specific number of satellites to be able to get a position. And again, when you look at brochures for different receivers, I don't know if you've asked yourself this question that they say that your receiver can be able to consume like even 296 satellites. Some are looking at 700. I think the highest I've seen so far is 900 plus, even 1,000. They're saying a GNSS receiver is capable to get constellations of more than 1,200. If you look at, the question is, if you ask yourself, they say the GNSS receiver can be able to consume 1,200 satellites, signals. If you look at the sky, we have the GPS, we have the Galileo, the GLONASS, they do, and all that. And then you ask yourself, how are these 1,200 coming into play? Remember, we have L1 as a type of a frequency. We have L2, L2C. So you find that one receiver or one satellite can be able to give you different kinds of corrections. These corrections, they have a purpose. one can penetrate. That's why you see there's a certain receiver that if you use can effectively work better under a canopy, but another one cannot work under a canopy. So then comes the issue of the having a receiver that can be able to tilt, another one cannot be able to tilt. So the moment you tilt it, or if you are in your office or in your house, you have a handheld GPS, you put it next to a window, it is going to be exposed to a specific part of the sky because you have a roof over your head. So that part of the sky that is being exposed to, it is that small section. So that is what we say. If it is completely exposed to the sky, we say you have a good dilution of precision. If it is partly exposed to the sky, then you have a poor. So PDOC, when you look at the GNSS receiver when you're working with it, you're going to something called like the GDOP, the VUP, and so on, the H. Okay? So it shows you the distribution of the satellites in the sky. And that is what it relates to the zigzag manner. So at the end of the day, when you undertake the course, you're going to learn what you can take about it. When it's advantage to use the flow station for vertical, the same question I was being asked, and how to set up to use the flow station for levels. Then you also need to understand the planning of the towers and the GNSS observation for optimal results. You're going to look at the GNSS data when you collect it. Is it just Trinex? Can you open that Trinex? Yes. Can you go to look at, was there a cloud at that particular time that you're making observations with your data? If there was no cloud, then what? So there's much more to be undertaken in the course. As I said, our courses, we are not in, of course, we tell you how to work with equipment. How to work with the equipment, we can teach you for 2 days. When you go and practice how to work with the equipment for the next 1 week, you'll be good in working with the equipment. But the question is, the parameters that are key in the equipment, that are the fundamentals aspect of it, so that you can be able to go out there and change them yourself, depending on the work that you're doing. So up to that point, we've covered the fundamental that is in surveying. So on the other end is a colleague of mine who will be taking notes of your questions. So if you have any questions, the chat box is open, and then after this presentation, I'll be able to respond to them. So you can put your questions on the chat box as we look at the fundamentals of AutoCAD. So we have a course called AutoCAD Civil 3D for surveyors. This training, we specialize or we focus on training surveyors on how to use AutoCAD to meet their daily needs. We've realized that surveyors use the GIS software to process survey work. But there's a reason as to why we have a CAD software. It has not been abolished by the manufacturers. And to make matters worse, or to make it more interesting, every single year, new versions of this CAD software still come out. And that is why an architect will always stick to AutoCAD. So this is an engineering course, and there are links. A surveyor can work with a mechanical engineer. A surveyor can work with a civil engineer. A surveyor can work with an architect. A surveyor can work with a planner. A surveyor is one person who can work with all, probably, engineering fields. And for them to be able to work uniformly, there's that one software, one language to be able to consume. So GIS is good, yes. For presentation, GIS is just a visualization tool of your work. But the core environment where you can be able to share your work with an AutoCAD, share your work with a civil engineer, do your volumetric analysis. comes the AutoCAD for that. When you join the course or when you decide to undertake the course, we focus specifically on functions that suits your need. It is a wide course, yes, but our interest is to focus on your daily needs and to come and say that, hey, EcoSpace, this is what I need, this is what I do, and this is what I want to focus. So we focus specifically on that. If it is a pipeline workflow of, I always do ABCD. So I want to know if I take it from here, how do I go to here? How do I get this spot? So we sit down, you understand your need, and then we tailor make the training to suit your need. So some of the fundamental things you need to know when you're using AutoCAD, you're building the system, similarly to what you define on the other. Nowadays, systems are interconnected in the sense that if you are drawing in an environment that is not properly defined, then it becomes very easy. It becomes very hard for you to share your data with others. So coordinate systems very key. I've come to learn that most of the surveyors that I have worked with or I have trained is that they save their data or they work in the sense that I go to the field today, I have my X, Y, and Z. I import it into the CAD, do my sketches, connect the dots, scale my drawing. What am I going to save? I am going to save the drawing. I am not interested in the box. I think they're looking at it in a wrong perspective. This course will train you how to create a geodatabase, or I call it a spatial database, whereby we store our main input, our main thing, the X, Y, and Z. We store the X, Y, and Z in a certain station or a certain database. Then now when you're going to draw in your CAD drawing, you are supposed to call for those points where they are. So that when you are done drawing, if you are going to share your data, the database is still maintained. When you need it next time, you can always still extract them and use them. So the moment the database is defined, so which means your environment where you're working on must also comply the same coordinate system which your coordinates are already predefined. That's the importance of having a spatial database when you're using your CAD software. The beauty of that is also it enables you link your drawing to other spatial or the GIS systems. Then, of course, you avoid the projection shifts that will happen during that. The takeaway to this is that it is you master most of the critical fundamentals for the digital surveying. This is very key. In CAD drawing, this is one of the key things that somebody should be able to know. Apart from just that, there's another one called the layer management. We are used to bringing, of course, I'm making this reference to the people that I've trained, people that I've worked with. We're used to bringing our cards, our data, especially surveyors. We bring our job into the system, we connect, we edit them one by one. When you're done, when you're doing, let's say you have even 1,000 points, you want to draw parcels, you want to join points one by one. It's time consuming. You want to do editing one by one. And the way this problem coming in, the problem is coming in because how the data was plotted. So by organizing your work or by using layers, it helps you organize your work and how you create your features. I want to create a road. I want to create a polygon. I want to create a contour. If I'm going to change the color of one, if I'm going to change the color, if I have thousands of roads, am I going to change the color of those roads one by one? No. I just go to one layer, I change the color of that layer, everything is changed. If I want to change the drawing readability, I want to edit it, I want to change the presentation. I want to change the symbol. I just go edit one symbol, apply to the layer. Everything I have the same symbol. It also helps save time. So what do you take away from that? It is clear that you create every feature in its own layer. If I want to draw a road, I first of all create a layer called roads. Then anything that I'm drawing that's called a road is under the road. There's something called smart codes. It's very easy for you to be able to draw points. That's what I'm saying. If you have thousands of points you want to join, you spend the entire week plotting. Yet this is something that you should draw within 1 hour out of from field. The next day you are done, even if there are 100 plots. How do I do that? I use smart codes to improve on your work and deliverables. Another thing that is key, and I don't know if people use it, is the satellite imagery. As a surveyor, you've gone to the site, you've done your work, you bring back, you've joined the points. It is important that you have the satellites in the background for background verification. It also helps you for the reporting, doing some reality checks that you might experience. So the question is, how do I add that? When you join the class, we're going to help you get a high resolution satellite background with them for your work. And doing the digitization, you can be able to actually have a feel that this is exactly where I was and where I was working. And of course, it improves the visual appeal and authenticity of your drawing. As we say, it's good, and then for the client reports. Another thing that is always of key interest is what we call scaling and plotting. Of course, there's a difference to that. It's not. There's a difference between scaling and plotting of your work. And I might say that I have to say that this is one of the challenges that I have experienced, that I have come to learn that many people have, especially when it comes to scaling. You've done your work perfectly, and then when you send it to that lady or that guy who does for you your plotting, then they give you something that is back wrongly. So when you put your scale rule on the paper, you get that the distances do not match according to the scale that you've indicated there. Surveyor of Kenya recommend you use Form 3 and Form 4. So join our class for the AutoCAD for surveyors. You're able to handle all this so that next time you don't have this challenge when coming or when working with your data. As I always say, I can see our time is up. So this is the last point, and in the beginning I mentioned that there's a lot that we need to discuss on this. Because as I said, we started from tape. Our good fathers used tape. There was theodolite. There was total station. We are in total station. It's being phased out slowly by GNSS. After GNSS, nowadays there are drones, left, right, and center. We have scanners. We are using the 3D scanners to do sectional properties. Then hence the importance of looking at the 3D data, modeling and management. So if you look at that evolution from tape to where we are right currently, it is very important that we give a preset of what is important or what you expect to see when you come to 3D data modeling and management. So we are going to create another session again, where we are just going to handle on the 3D data modeling and management. And these are just some of the things that we are going to cover in that session. So how do you turn your point clouds? Of course, we are going to discuss how point cloud can be created from the satellite images, where we have something called the stereotype kind of image. So how do you turn your point clouds data and survey point into surfaces, terrain models, building models, visualize the projects in 3D? As I said, when I'm doing sectional property, I have a 3D scanner. Within 10 minutes, I'm done. doing a scan of even a 3-floor building. Learn how to structure your field notes, especially when it comes to scanning. Then how to avoid data loss. Map projection, and that's where in this course we look at from the data collection to the data presentation of your work. Because the key thing actually with us engineers is always the presentation of our work. You can know something, but if you don't present it correctly, somebody might take you that you don't know whatever you're doing. So it is very key that we learn how to document our work in a professional manner. So I hope your questions are in, and up to that, we are running a discounted course training on the issues that we've raised. So we have a 30% discount for the first 30 registrants. That is on the GNSS data processing and manipulations using TBC's Trimble Business Center or Tech. So Trimble Business Center is a paid license. Tech is an open source, which we also train people on how to process data with this course. The fact that it's open source, the smart that you need to learn about it. Then we have a course called Drone Data Processing and Analysis. Flying a drone is very easy. You fly the drone, you have the images. How do you extract information from that image? How do you make good use of that image? And how do you give it to a client to justify that exactly the volume of that heap is this? We have the introduction to and surveying using the GNSS receiver, of which we just looked at a preview of what you expect on that course. Similarly, we've also talked about the fundamentals of AutoCAD Civil 3D for surveyors. So this is still open for registrations. So anybody who is interested can be able to log in and register for the course. So to reach us out, that is the address and the email address, phone number, and now you can reach us. So up to that particular stage, I don't know if there are any questions on the chat box for me to respond to. All right, I see there is no question on the chat box. Okay, thank you for listening and thank you for joining. So I'll leave the meeting still open for the next 10 minutes. So if anybody has a question, anybody want to ask anything, you can send an email on the number, on the email address shared, or you can as well send your question on the chat box and I'll be happy to respond to it. Thank you very much and have a nice afternoon.